Hello, hello, and welcome to this video of multi-threading in C using POSIX threads. So far, we have covered the thread creation, thread description, and mutexes and condition variables, and how we can synchronize and share data using mutexes and condition variable. So that forms the core of the multi-threading. You acquire a mutex and you change shared data, and then you signal a condition variable, and some other thread who is waiting on that shared data gets access to that data, and that thread works on it. And I have talked about thread per core architecture earlier. So in this PDF, we will see some more ways to use thread. Okay. So this is quite a bit long PDF, 45 pages, as you can see. So we may not be able to cover all of it in one video. It might take two videos. The first thing is architecture at a glance. So there are usually three ways to work with threads. You can structure using a pipeline, work through, or client server model. Okay? You will see that thread per core will also come into this. Okay? So pipeline is data moves through a sequence of processing stages. Think of an assembly line. So one thread is doing something, it does something with one piece of data, then it passes on to another thread. That second thread does its own thing, then it does its thing and passes on to third thread, and so on. So these are sequential in nature. One thread works at a time on a piece of data. Then you have work through. Many threads perform independent pieces of the same larger job. Okay? This is what thread per core architecture does actually, kind of. Okay, you have as many threads as your CPU. That is the computational threads. Other threads are separate, and each thread is doing its work. It may be the same work, but they are independent in nature. And whenever you have to share data, you do message passing. Okay, in this case, the pieces are independent, so you don't need to take locks. Okay? That is the uh, key distinction it has. Then we have client server. Threads handle requests from clients, often sharing the service resource. This is typically used in a network server, for example, a web server, a mail server, a database server. So network servers usually do this kind of client server model. For example, Postgres uses multiprocessing architecture. So for each connection, it spawns a new process, and that is kind of debated for in the community for a long time, that Postgres is inefficient in its architecture, but it is quite old and it is what it is. Then these are the three recurring designs which you will see. So this we have this. So the question is not only that how do you create more threads. Creating more threads always does not result in efficiency. In fact, the efficiency may go down if you spin more than certain number of threads, and lock contention will always be there. Right? So why do these three models matter? So in pipeline, data flows through stages. In work through, tasks are distributed, and in client server, requests meet services. So this is the same pizza API, and it can support these three architectures. And first we look at the pipeline. So you know the basic idea. You have some input data, it goes to stage 1, stage 2, stage 3, and output. Each stage can be implemented by one or more threads. The output of one stage becomes the input of the next stage. The slides are pretty simple. So it's the same diagram. Okay. So when does pipeline architecture is good? So the obvious answer is that computation should have natural sequential phases. Each phase can operate with another phase is processing a different item, and buffering can decouple neighboring stages. So suppose an item requires three operations, operation A, B, C. With one side, item moves through stages sequentially, with three stages running concurrently, so how this would look like in picture. So at time t1, item 1 is in stage 1. At time t2, item 2 comes in stage 1, item 2 goes in stage 2. At next point in time, that is t3, item 3 comes in stage 1, item 2 goes in stage 2, item 1 goes in stage 3, and so on. So the first result takes roughly 3 stages to merge, but throughput can become much higher. Okay? Because the thread which is on any of these stages, stage 1, stage 2, stage 3, they are not sitting ducks at any point of time. They are always working either on item 1, item 2, or item 3, item 4, or so on. So suppose that we have, say, 3 stages, and if you are single thread, then the output would be triple here. If you have n threads, then output would be, throughput would be n times. So the mental model is given here. So thread A is there, it works on Q1 and then pushes on to thread Q2 where thread B works and then thread C works. So Q provides hands off between stages. Synchronization protects the queues and coordinates when producer and consumers may proceed. Now we look at pros and cons of this design. Natural decomposition for stage processing. Multiple items can be in flight. Each stage can be optimized independently and it is useful for streaming data. Now the cons of this is throughput is bounded by the slow stage. Queues add latency and synchronization overhead. A badly balanced pipeline leaves threads idle. Shutdown and error propagation need careful design. So something I'll talk about this limit of a badly balanced pipeline leaves thread idle, when that will happen. Okay. So suppose stage 1 takes 5 seconds. Okay. Stage 2 takes 10 seconds and stage 3 takes 15 seconds. So in stage 1, thread 1 is producing roughly at double the rate of stage 2 threads. So you need 2 threads of stage 2. And stage 1 is 3 times, outputs at 3 times compared to stage 3. So for stage 3 to thread, for each thread of stage 3, you need 3 threads of stage 1. So balancing it becomes difficult. So how do you balance it? So you have 3 threads of stage 3. You have 2 threads of stage 2 and 1 thread of stage 1. That way you can balance it. If you don't balance it that way, then thread 1 will become sitting ducks after some time. Okay? Because it is the fastest thread. So it will finish its job very fast and then it will wait. That I can give you an example of what can happen. Okay. So suppose we have a queue where we are going to enqueue the data. So for simplicity, let's assume there are 2 threads, thread 1 and thread 2. Thread 1 completes in 5 seconds, thread 2 completes in 10 seconds. And there are only 2 threads, 1 thread for thread 1 and 1 for thread 2. And the queue can hold, let's say, 10 items. And after first 5 seconds, the first thread will complete its first item and put it in queue. And at that moment, thread 2 will wake up and start processing item 1. At the same time, thread 1 is processing item 2 and it will push in the queue after 5 seconds. So at this moment, thread 2 has not yet completed. It has completed only 5 seconds on item 1. So in the next 5 seconds, thread 1 will pick up the third item and enter in the queue. At this moment, thread 2 will see that, okay, I finished with item 1 and it will take up item 2 from queue. And in the next 10 seconds, thread 2 will process item 2, but thread 1 will enqueue 2 items. So you see, at this moment, the queue has 3 items. So the number of items in the queue is increasing. and eventually queue will become full. Queue does not have infinite capacity, right? It has to have finite capacity. So eventually the queue will become full, and thread 1 can't push another item. It has to wait for an item to be removed before it can include another item into that. So thread 1 will be sitting up there. So that's that. And throughput is bounded by the slowest stage. So as I explained, the case of 3 threads, although throughput is bounded by the slowest stage, if you have computational power, you can spin more threads. That is usually not a problem. But still, if you just want to measure throughput on the basis of the time computation, then you assume that a pipe is there and there are what you call the pipe is has variable diameter at some points. Some point its diameter is small, some point it's big. So let's assume there are 3 cases where diameter is narrow. Then the amount of water flowing through the tube will be governed by the narrowest portion. Okay, and it doesn't matter how big your biggest diameter is. That does not control the flow of liquid in that. What controls the rate of flow of liquid is the narrowest diameter. Now, in this case, the example of thread 1, thread 2, thread 3 will actually govern how fast your items can process. And since you have to have queues to hold the items which cannot be processed yet, so it adds minor latency and synchronization overhead, and shutdown and error propagation need careful design. So what can happen is that thread 1 might encounter an error. What do you do then? Okay, how do you continue working on next item and so on? And when thread shuts down or thread 2 shuts down, how do you manage that? So these things you have to take care of. Now, those are pretty simple and straightforward to understand, and I think you can understand that very easily. So I will not go into that. So the question is, can different stages work on different items at the same time? And the answer is usually yes. In a well-designed pipeline, yes, those can work. Now we will look at work queue. Uses several threads to perform many instances of the same kind of task. Instead of assigning a permanent stage to each thread, threads repeatedly obtain work. Okay? So you have work queue and you have threads which will work on these and they will get the result. Now imagine 10,000 independent tasks, and a serial program will perform task 1, task 2, task 10,000. The work queue can divide the task dynamically. Okay? In fact, you don't need to divide the tasks actually. Okay? What can happen that each thread will do 10,000 works, all tasks. Okay? I'm giving the alternative design and what is written here. Each thread will perform the same serial task, but now we have 4 threads. So 10,000 independent tasks by 4. Or assume that you have one serial program and now we have 4 threads, and each thread is performing these tasks in serial, so you have 4 times throughput. Now the architecture which we described here is that tasks can be split. Thread 1 can do 159, thread 2 can do 2610, thread 3 can do 3711, and 4 can do 4812, and so on. Dynamic assignment is often better than static assignment when task durations vary. Okay? Now that's why I said the task duration can vary and threads can become idle here. Okay, that is why let each thread do all the tasks and you just give entire 10,000 tasks to each thread. So if you have, let's say, 100 items, each requiring 10,000 tasks, you give 25 items to each of them. So that is what I was doing. And the common design is a protected queue. While there may be work, you acquire lock on queue mutex. While queue is empty and not shut down, you wait for the queue condition and queue mutex. And if shut down and queue is empty, unlock and break. And then you remove task from queue, unlock mutex, execute task. So the key idea is that mutex protects queue state and not the expensive task itself. Now we consider 4 tasks, 1, 1, 1, 10. So static assignment can produce 1, 1, 1, and 10. 3 threads become idle while one keeps working. This one is time taken. The work queue lets an idle thread acquire another task. Okay. So this is the central lesson of the work queue model. Distribute work dynamically when the cost of individual tasks is unpredictable. Now we have the pros and cons of queues. So it is very good for many independent tasks. It is natural load balancing. Threads can be reviewed instead of created per task. The same architecture can serve many workloads. The queue becomes a synchronization point. There is a limit. Any task may cost less than scheduling overhead, and I told you how we can overcome that. Shared output still requires synchronization. Too many threads can reduce performance. So these are the limits and strengths of the work queue model. Okay. And before we go into client server model, I think I can stop here and let me discuss some of it. For example, so I'll take an example. Okay. So the natural idea is that let me go to that slide. Okay. So you see that you have thread 1, thread 2, thread 3, thread 4. So usually you don't do this. Okay. I'll give an example. Suppose you have a thread pool, all right, where we have, so it may be dynamic, static, whatever, doesn't matter. And say you have 32 threads, each running on each core of the CPU, and it's a web server. So the master thread receives a request from the client. It goes on receiving the thread request, and then it assigns the thread to thread 1, thread 2, thread 3, and so on up to 32 threads. And threads perform the execution. Usually HTTP work is not multi-threaded, so we will not go into each request being multi-threaded. We will assume that each request can be handled by thread one thread only. So thread 1 will process one request and returns a response, and thread 2 will receive another request, returns a response. So you see that your work is being distributed to all the threads, and they are performing all the tasks in kind of concurrent manner. Okay, or they can even be parallel. It depends on the situation. So you naturally, when you design worker threads kind of stuff, you don't do this kind of design. So that's what I wanted to explain about the thread. Now you would say that so what is the advantage of doing this work, this kind of work? So the advantage is that you don't have a queue state here anymore. The requests which you are receiving, you're not putting them in a queue. Okay, and the threads are not picking up the tasks they are being assigned. There is another thread there other than these threads, a master thread, which will handle the assignment of tasks there. Okay, so you eliminate this queue here. You don't want to have this queue. This queue is held by the master thread. Okay, no other threads has access to this queue. So that is one way you can define the work queue. That is the typical thing you do in client server model. Okay, as you will see in the next video. So I'll stop here and we will discuss more about architecture of threads and how we can implement multi-thread programming into different architectures. So we will look at client server architecture in the next video, and possibly we can finish this presentation. So I hope that you enjoyed this video and learned something. So I'll see you in the next video with the client server architecture, and finally we will compare all three models and see how we can work with them. So thanks a lot for watching the video, and we will meet again after 4 days with another video on multi-threading using C programming and POSIX threads. And the thing is that this architecture you can take anywhere. You can take into C++, you can take into standard threads of C, or you can take it into Java or any multi-threaded programming concept. The concepts go everywhere. The syntax and the function calls will be different, but the main idea is that. So thanks a lot for watching the video. I'll see you in the next one. Till then, stay curious, keep learning, and most importantly, enjoy.